Hello and welcome to Module 3 of the Consilium Aquis Sulis course on railway signalling. This module describes the evolution of railway signalling from the steam age to the information age. It begins by describing the origin of railway signalling in the steam age of the 19th century. It then describes modernization of signalling in the 20th century, before presenting the information age technologies of the 21st century. Early railways did not have signalling systems. Train movements were instead controlled and authorized by policemen. After a train had entered a section of track, the policeman waited a certain period of time before allowing a subsequent train into that section. This was known as time block operation. Policemen were also responsible for moving points to cause trains to take different paths over junctions. However, this method of controlling trains had a number of serious risks. Time block operation doesn't guarantee that a train is a safe distance ahead when another train is authorized into the same section. The first train may have broken down, derailed, or been forced to stop before an obstruction. Points could move underneath a train. The policeman could make a mistake. In the wake of a number of serious accidents, the Regulation of Railways Act 1889 mandated the block system, whereby railways are divided into block sections into which a train cannot be authorized until the previous train has left. Continuous self-applying brakes for passenger trains, and interlocking of points and signals. Other legislation mandated facing point locks to hold points in place as trains passed over them. These principles remain with us today. However, the technology through which they are implemented has changed drastically. Initially used only for communication between signal boxes at either end of block sections, electricity saw wider application in the 20th century. Mechanical semaphores were replaced by electric color light signals. These could be placed further from their control location to accommodate longer stopping distances and hence higher speeds. Electric motors replaced human muscle power as the motive force for points. This made longer points with larger radii of curvature on diverging paths possible, and hence higher speeds on those diverging paths. Electric train detection enabled block sections to be automatically proved clear of trains without signaller action. Electric relay circuits automatically commanded points and signal aspects. Rather than physically moving points and signal aspects, signallers simply requested routes from one signal to another. This higher level of automation enabled an individual signaller to control large and complex areas from a signaling control centers. Towards the end of the 20th century, relay-based interlockings started to be replaced by more compact computer-based interlockings. Push-button control panel similarly gave way to computer-based control systems, capable of setting routes automatically. The late 20th century also saw the advent of comprehensive automatic train protection. Comprehensive ATP mitigates the risk of driver error by continually supervising speed to prevent trains traveling further or faster than authorized. Some ATP systems can also provide cab signaling. Instead of authorizing trains to move via mechanical or color light line-side signals, authorizations to move are presented in the driver's cab. Cab signaling overcomes the spacing and sighting limitations of line-side signals and can be used to enable trains to travel at higher speeds, increase the capacity of a line, and reduce costs by avoiding the need to construct and maintain line-side signals. The information age of the 21st century brought standardization of ATP and cab signaling through the European Train Control System, radio-based transmission of signaling data using radio block centers, and even greater centralization of control in rail operating centers. A further extension of cab signaling, supported by the most recent ETCS standards, is automatic train operation. Signaling authorizations are not only presented in the driver's cab, but trains are driven automatically in accordance with those authorizations. ATO enables improved capacity by providing a consistent driving style with high braking rates. ATO also enables dynamic regulation of train speed by a traffic management system, offering a number of potential benefits. Optimization of capacity at junctions and station platforms, reduced wear and tear and energy usage as trains do not travel faster than needed, and improved safety as trains tend to travel at lower maximum speeds and approach conflict points less frequently. Some of these benefits could be realized without ATO by presenting advisory information to drivers using a connected driver's advisory system. In summary, key principles of railway signaling introduced in the steam age and still fundamental today are the block system, continuous self-applying brakes for passenger trains, interlocking of points and signals, and facing point locks. 20th century modernization introduced electrically powered signals and points, enabling higher speeds. It also ushered in ever-increasing levels of automation and centralization of control thanks to electrical train detection and relay circuitry. Computer-based signaling, comprehensive automatic train protection, and cab signaling started to be introduced in the later part of the century. The information age of the 21st century has brought standardization of ATP and cab signaling with European Train Control System, radio-based transmission of signaling data, and the advent of automatic train operation on mainline railways.